So this is our first flipped lesson, and this is going to allow us to spend a lot more time in class working through problems together and really figuring things out. So chapter one hopefully is mostly review, but if not, make sure you're coming into office hours and asking questions. I would also go ahead and write down notes just like you were taking notes in class. And also make note of any questions you have. So you can ask either in class or you can go ahead and send me an email or send me a message through Remind. So chapter one deals with keys to the study of chemistry. So really this is going to be the foundation for everything else that we're going to build on. Matter is going to be basically anything that takes up space and has mass, so pretty much everything around us. And throughout the semester, we are going to classify matter and characterize it in different ways. So the first way we're going to look at it is how it changes. And we can break that down into two different ways that matter can change. It can either undergo a physical change or a chemical change. So I have some examples of both cases, and the first one is going to be a physical change where, for example, ice is melting, or we take a piece of paper and we're crumbling up. The key here is that whatever the substance starts as, it also ends. So even though we have the cube, it's H2O molecules, and then once we melt it into liquid water, it's still going to be H2O. So even though what it looks like changed, the actual substance itself is not changing. Same thing for the piece of paper. Even when we crumble it up, its chemical makeup is exactly the same, and that's why it's called a physical change. A chemical change, on the other hand, is where we start with one substance and we end with something completely different. So here's one example, one of my favorite demos. This is the exploding gummy bear, where you take potassium chlorate and you heat it up to do a decomposition reaction, which we're going to review in a few chapters, and you produce potassium chloride and oxygen. And the oxygen mixes with the gummy bear, basically sugar, which is it's going to act like a fuel just like in your car. And it's going to undergo a combustion reaction and you produce carbon dioxide and water. So you have carbon dioxide here and water. But the key here is that we're starting with these two substances and we're ending with something different. So matter actually changed and transformed into something else. Another way we can classify matter is by looking at its properties. So we already looked at chemical versus physical change, but now we can look at physical properties versus chemical properties. So the way we define these is a physical property is going to be something that can be demonstrated, but without actually changing what the substance is. So things like malleability, where I'm forming usually a metal into sheets, or how ductile something is, where I can stretch it into a wire, but the substance again is exactly the same. It hasn't actually changed. Or something like brass, where it can be melted and it changes forms, but the substance itself is not changing. So some common examples are going to be density, melting point, or boiling point. These are going to be physical properties. I don't actually have to change what the substance is to demonstrate that property. A chemical change, on the other hand, is going to be where I have to take that substance, and when I am displaying that property, I am converting it into something else. I actually have to undergo a chemical reaction to display that property. So we have a few examples here. Okay, so you can take a look at those. Right. One thing we want to talk about is also energy. So over the course of the semester, we're going to see that energy is going to interact with matter, right? So because of that, we want to define different types of matter. So, or rather, different types of energy. The first one is going to be potential energy. So if I am at the top of a high mountain or at the top of the stairs and I'm holding a ball over it, that is a lot of stored up energy. So that's going to be called potential energy, energy that's stored. And then when I release it, that potential energy is released or transformed into kinetic energy or energy of motion. So why do we care? Why do we care about this? Okay, so again, matter is going to interact with energy, but really we want to think about a few things, right? We want to make a few connections. Lower energy is going to correspond to something that's more stable or favored. We're going to learn later on that something that is high in energy is going to be less stable or unfavorable. Okay. So if we think about chemistry, the whole point of doing chemistry is to become stable. All right. When we undergo a chemical reaction, we want to go to something that's more stable. Right. So the way we can do this is by either making and breaking bonds. So that's one way to become stable. And we're going to talk about that a lot more when we get to chemical reactions. And also by gaining and losing electrons. So we'll talk about some redox chemistry, but in the back of your mind, I want you to continue to think that everything is trying to get to stability. Okay, everything wants to be stable. So again, if we think about something as simple as a positive and negative charge, when they're far apart, this is going to be less stable. All right, so it's going to be higher in energy. And then once they come together, plus is attracted to minus, that's going to be a more stable state and is going to be lower in energy. Okay. Really what we're getting to, where all of this is going, is that potential energy is going to be stored in bonds. So anytime we're doing or undergoing a chemical reaction where we are breaking bonds, we're essentially releasing that potential energy and we're able to use that to do work or form new bonds. Right? Another way we can think about this is chemical energy. For example, the food we eat. I love to eat, right? So as we're eating different things, our body is going to be transforming that potential energy by making or breaking down those bonds in the foods that we eat and transforming that into chemical energy. Right? Another concept that we're going to think about a lot this semester is the difference between accuracy and precision. So first, I want to just demonstrate with the bullseye what that means. Okay, so if we think of a bullseye, our goal is to hit the center. That is our target. So this is going to be accuracy when we actually hit the target in the place we want to. Okay. If we think about how this translates to what we're going to be talking about, accuracy is how close my value is to a known value, right? So I'm comparing my value to a known, right? If I look at precision, notice that I'm not hitting the center of the bullseye, so it's not accurate, but I do have all of my hits in the same general area. So if I look at where all of them hit, they're in the same general area. So I do have precision, right? So another way that we could describe precision is reproducibility. So even if I'm not accurate, I can be precise by getting the same value over and over, right? Something I would do is pause the video and think about how this is going to translate into a laboratory situation or working in a research lab. Why do you think something like accuracy and precision, why are they going to be important? And why are we going to continue to see these themes throughout the semester? Right, so we can look at all the different combinations. If we think about if we have our target and we have a lot of shots, if we have all of them right at the center of the bullseye, well, that's where we want to aim. So that's going to be accurate. And notice that all of my marks are in the same general area. So this is also going to be high precision. If I look at the next bullseye, I'm not hitting the center of the target. So I have low accuracy. I'm not actually hitting where I want. Okay, but notice that all of my hits are in the same general area. So it's similar to the example we saw above. In this case, I do have very high precision, right? In the next one, I'm getting pretty close to the center of the bullseye with all of my hits. So I do have pretty high accuracy, but notice that not all of my hits are very close together. They're a little bit more spaced out. So that means my precision or my reproducibility is not as good. So I have low precision. Now, if I have hits that are all over the board where they're not at the center where I want to go, that means I have low accuracy. And they're also not in the same general area, that also means I have low precision, right? Something to think about again is how would this translate to a real life application? Why would accuracy be important? Why would precision be important? We can talk about this in lecture. So something to think about now is you are going to be doing a lot of recording data in the laboratory, and then you're going to be processing that data, and we're going to be doing a lot of graphing in lab. So Excel is going to be your second best friend. I like to say the periodic table is your first, but become familiar with Excel. It's going to make your life a lot easier. Right? So if I look at the plot, I'm looking at different trials. So I'm doing the same experiment multiple times, and I am measuring the mass of water. So I have the mass in grams, and if I look at all of my values, they're all right around 25 grams. So they're all pretty close together, right? So I'm definitely precise. And assuming that the mass that I'm aiming for is 25.0 grams, I'm also accurate. Okay, so the accuracy again is how much it actually weighs, right? Let's look at the bottom. We have the same thing where we have the trial number, okay, and the mass of water, the actual mass that we're aiming for is going to be 25 grams. So we have that 25 grams shown on this line. And we're getting right around 27 grams. So one thing we do have is that we're consistently getting around 27 grams of water. So it is going to be precise because I am reproducible, but it's not going to be accurate. Okay. One thing we want to think about is instrumentation. So if we look at two different instruments that are used to weigh materials, we have a very old school, I know we're taking it way back, we have a triple beam balance on the left, right? And then this nice fancy analytical balance on the right. And if we think about precision, it's going to depend on the instrument. Okay, so the reproducibility of that measurement is going to depend on, well, what tool I use to take that measurement. So if I have something like a triple beam balance, when I record my value, I can say 1.5 grams. Now, if I have an analytical balance and I weigh something, it's going to spit out this much longer number. So now I can say 1.5321 grams. So let's go ahead and make that connection. We're going to talk about significant figures, and hopefully you've taken a look at that video, but if not, go ahead and take a look at it and we'll talk about it. But this one has a higher number of significant figures. So I have 1, 2, 3, 4, 5 significant figures here. And in the first value, I only have 2 significant figures. So we want to think the more significant figures we have, the more precise our measurement is. So we can also just look at the number of significant figures and it tells something about that instrument used to make the measurement. Right? So two things that are associated with this are going to be a systematic error. Okay, that means that all the values are either higher or lower, or we can have a random error where values are both higher and lower. It's pretty unpredictable. So it depends on the instrument. So another way to define precision is going to be a measure of uncertainty. So it has to be a measurement that you're taking, but you're figuring out the amount of uncertainty in that measurement. So if we look at this in the laboratory, if we want to look at the difference between a random error and a systematic error, again, the random error is going to be where, again, you have different trials because you want to look at precision, you want to look at reproducibility and accuracy. So again, our aim is 25 grams if we're measuring the mass of water. And some of our values are above, some of our values are below. It's random, right? Whereas a systematic error, it's consistent. So all of our values are higher than what the value should be. So again, this depends on the instrument, and for the systematic error, maybe its calibration is a little bit off. So that would lead to it consistently being higher or lower. Whereas a random error is more of what you're doing in the lab. So something I would do now is go ahead and make note of any questions you have. Hopefully you took some good notes, and you can go ahead and either email me or send me a text message and remind, or bring those into class, and that's where we'll start.